Unit 5 involves Chapter 7. Okay, so I know that kind of sounds strange, but we're going to go through 3 sections in Chapter 7. It's going to be very exciting. What we're going to talk about this week is the area between curves. And then next week we're going to talk about volumes of revolution and volumes by slicing, like slicing brick, okay? And that's what's going to take us up until spring break. Now, we're going to be doing a lot of integrals. This is the application of integrals unit. This is only like half of what's in Chapter 7. Those of you who go on to like a Calc 2 class, you'll learn more applications of integration in a Calc 2 class. But this is where we're going to start. Okay? So, let's go back to what we learned in Unit 4. Okay? Don't write this down. This is what we took a test on the other day. Right? When we added up all of the rectangles underneath a curve, it represented the area underneath the curve. Right? We took the width times the height of these rectangles that are infinitesimally small. What is infinitesimally small? What would that be?
Infinitely, is that what it means?
Yes. Infinitely small. Would that be a better way to say it? Would you like that? Okay, infinitely small. Okay? Now what we want to do is we want to find the area between 2 curves. So we're no longer going to find just the area under one curve. We want to find the area between 2 curves. So I'm going to draw a picture up here, and I want you to take 30 seconds to describe how you think we are going to find the area between 2 curves. 1, 2, 3, go.
And then reveals around yeah, you correct. The smaller one more.
Okay, class 3, back there. Ideas? Larry?
Find 2 intersection points.
Okay.
Plug both intersection points into like each antiderivative, and then
Subtract something. Okay. You're in the right direction. Are those intersection points going to be important?
Yes.
Very important. Okay. So you're on the right track. And I like what you said with subtraction. Pod 2, what were you guys talking about?
I was thinking along the lines of we take the area under the curve for one of the functions and the area under the curve for the other one, and over the interval from the first intersection to the second intersection, we subtract them.
Okay, so Connor is kind of going off of your suggestion here. He's saying take the area of one, take the area of the other, and subtract them. Visually, what do you think about that? Right? We can take the area from here to here. We would have to find, it would go all the way to the x-axis, right? So then we'd have to subtract the area underneath that bottom curve to give us the area in between. That's exactly what we are going to do. In order to find the area between 2 curves, we have to subtract the area of the smaller curve from the area of the bigger curve. Okay. Right now, this is written as 2 separate areas being subtracted, but what we can do is we can write it as one integral to save us some time. Okay, now I do want you to draw this picture, and every time we find area between two curves, you have to draw its picture. Okay, first of all, we need to know where we have any intersection points. Okay, second of all, we need to know which function is bigger than the other. All right, what I'm going to have you do, okay, take a time out real quick, I'll come back. Integrals mean we're adding up these infinitely small rectangles, right? So what I'm going to have you do with each area that you find is draw in one infinitely small rectangle. So you can see where the rectangle has its highest and lowest points, okay? So when I look at this rectangle, I know that the top of the rectangle rests on f of x, the bottom rectangle rests on g of x, and so I know I need to take f minus g. Sometimes I like to describe this as top minus bottom function, okay? Also, we're eventually going to get to the point tomorrow where we don't always have to go with vertical rectangles, okay? So I want you to draw in the rectangles, and since these are perpendicular to the x-axis, we're going to label their thickness dx. And that way we know that we are integrating with respect to x, okay? Right now, that's all you know how to do, but come tomorrow, we're going to open the doors for integrating with respect to y. And so we're going to need to draw those rectangles in and label them with what thickness they have so that we know what we're doing. Okay? So, it is as simple as taking one area, subtracting another area, but we have to know which one's bigger, and we have to have a picture in order to be able to do this. So, some of the practice is really about drawing the picture and figuring out the region. All right, so this is our first example. I want the area of the region bounded by y equals x plus 6, y equals x squared, x equals 0, and x equals 2. Now this is something that we do not need a calculator to graph, and I would expect you to be able to graph this region without a calculator. Okay. So, y equals x squared. Looks like this, right? Okay. We have the line y equals x plus 6. 1, 2, 3, 4, 5, 6. So here's x is 6. We have a slope of 1. Oh, sorry about that. Do you have a question?
No.
Are you sure?
I really don't have it.
Okay. And then we want x equals 0, which is the y-axis, and x equals 2, which is right here. Okay, there's a lot of stuff going on there, right? But for sure we need between 0 and 2 specifically, right? So the region in question here is between x equals 0 and x equals 2, and then between the parabola and the line. So it may be beneficial for you to lightly color in the region so you know the region that you're looking at. Okay. And then you're going to draw in an infinitely thin rectangle and label it dx since its thickness is really, really small along the x-axis. Okay? Now we can imagine where our top function is and where our bottom function is because it's sitting right in front of us. Okay? Now, it's pretty obvious to us which one's the line and which one's the parabola, but in the case where you have two parabolas, it may be beneficial for you to also label your equations, like labeling that this is y equals x plus 6, and labeling that this is y equals x squared. Okay? So, our limits of integration. Grant, what would they be?
0 to 2.
Okay, we are adding up rectangles from x equals 0 to x equals 2.
The sum of x plus 6.
Okay?
And then, should I just do divide them into 1 or
Mhm.
and then subtract x squared?
Yep. Okay. So we're going from 0 to 2. We're integrating with respect to x. So we look at where x starts and where x stops. That's at 0 and 2. All right. Our top function is x plus 6. Our bottom function is x squared. So we have x plus 6 minus x squared inside of our integral. This dx is important. If it's not there, the setup of your integral is not correct. On your quiz next week, half of it is just going to be setting up the integrals. Half of it will be actually finding the area. All right? If you don't have that dx, you don't get full credit for the setup of your integral. Do you understand? Okay. Now, would this be one that is overly difficult to integrate by hand? No, this is not bad. Antiderivative of x is 1/2 x squared. Antiderivative of 6 is 6x. And then x squared becomes 1/3 x cubed. And we're evaluating this from 0 to 2. Okay? This is one I would expect you to be able to do by hand. Okay? Because we have 1/2 times 2 squared would be what? 2 plus 6 times 2
12.
minus 1/3 times 2 cubed. 8/3. Minus, what do we get for all of those when we plug in 0? So now we need to know what 14 minus 8/3 is.
11.
What did you say?
11 and a third.
11 and 1/3?
Yeah.
Or 34/3? Okay? In your homework, and I'll tell you which ones, there are going to be a couple I'm going to have you do by hand, and then the rest you can do with a calculator. Okay? And that's what my expectation will be on the quiz and test as well. Some you'll have to do by hand, some you'll just have to set up, some you'll get to use your calculator to find. Okay? All right, how do we feel about it so far? Next one. Okay. More of the work is really going to come from drawing the picture and getting it set up, especially if we have to find intersection points, like Larry pointed out. Okay. All right. We want the area of the region enclosed by y equals x squared and y equals 2x. Here is y equals x squared. Y equals 2x. So we have a y-intercept of 0, slope of 2. Oh, that is... That is not my best line in the world, but will you forgive me? Thank you. Okay, and then I'll label this line as y equals 2x. You see me coloring there, right? Do I keep disappearing? No? Okay. All right. So then I'm going to draw an infinitely thin rectangle. Since it has thickness that would sit on the x-axis, we call that thickness dx. Okay, which tells us that we're integrating with respect to x, but that's all we know how to do anyway right now. Okay? What would our limits of integration be?
0 to 2.
Okay, how do you know 0 to 2? Okay, now, some of us can tell by the graph because we plotted the point 24 for both of those graphs. Okay, now, if it wasn't obvious to us, or we weren't quite sure, even though we graphed it, how could we find them algebraically? We would have to set them equal to each other. X squared equals 2x, okay? And then we would have to use our algebra. Okay, in this case, we would have to factor x equals 0, x equals 2. All right, this one was pretty obvious, but there could be times where you're going to have to go through all the algebra to get those limits of integration. Okay, so let's set this up. Our area is going to be the integral from 0 to 2. Isaac S, what's our top function? Okay, y equals 2x is our top function, minus our bottom function, which is x squared. Make sure the top minus bottom function all gets put in parentheses with the dx, because we're integrating all of it. Okay. Just to save some time, let's go ahead and use the Math 9 command in our calculator to get this area. What do we get? 1 1/3 or 4/3? Yes.
So does our graph picture, can it be just like a rough sketch? Or do we have to draw like the marking points and everything?
I mean,
Because I mean the marking points, I'm not a great artist.
I'm not either, obviously. Okay, do the best you can, but you need the picture so you know which function is on top and which function is on bottom. Okay, that's really where, in which quadrant it's in and those kinds of things. That's what the picture is for, okay? Do your best to do these pictures without a calculator, unless your book specifically says use your calculator to do it, okay? These are really more about how to set them up than the actual integration itself. But I don't want you to lose the skill of integrating, so we're still going to practice it throughout this chapter. So some of these we'll do by hand, some of them we'll do with the calculator. Okay? All right, next example. What, Cole? We don't need a graphing calculator for this one. However, we are going to have to get a little bit more comfortable with graphs like x equals y squared. What does x equals y squared look like?
Plug in points to draw these.
It's just a sideways bracket.
It is a parabola that opens to the right. Now, you need to at least recognize that it's a parabola that's not up and down, because it's y squared instead of x squared. Now, grant you plugging in random points to figure out where the parabola is, not a bad idea if you're nervous, but you need to recognize at least that that's a parabola opening sideways, okay? You'll actually have quite a few of these tomorrow, so that's just a warning, okay? Y equals, so this is x equals y squared. Y equals x minus 2. So our region is this one right here. Okay, now here's the problem. Our parabola is written as a function of y and not as a function of x, right? If we're going to have to integrate with respect to x, we need these to be a function of y. So if we take x equals y squared and we solve for y, what do we get? You're missing something.
Radical plus or minus radical less.
When we solve using a square root, we have to include the plus or minus. So this portion right here is y equals radical x, and this right here is y equals negative radical x.
So there are technically 3 functions instead of 2 functions.
Okay, now here's another issue. I'm going to draw my rectangle right here with thickness dx. What do you notice? Okay, that's fine because we wrote them as 2 different functions, right? But what about a rectangle that's over here? What's true about the bottom function with those 2 different rectangles? Is the bottom function the same? No, the bottom function switches right here at x equals 1. So since our functions on bottom are not consistent, we have to make this 2 different areas that we're finding and add them together. Okay? So for this area right here, from 0 to 1, we have the red function on top, radical x, minus the green function on bottom, negative radical x. Okay. Plus, what's that intersection point right there? So we need to find it using some algebra. Think so?
14.
How'd you get 4-2? Isaac, how'd you get 4-2? You graphed it? Okay. Is graphing an appropriate way to find 2 intersection points? Okay. As long as you check your work. Does 4 equal 2 squared? Yes. Does 2 equal 4 minus 2? Okay, 4, 2 is that intersection point. As long as you check to make sure they work in both, graphing is an appropriate way to find 2 intersection points. But if graphing doesn't work, you need to set them equal to each other. All right? So then we're going to add the integral from 1 to 4 of our top function is still radical x, but now our bottom function is that blue line, x minus 2. Notice how I put x minus 2 in parentheses because we're subtracting the entire quantity of x minus 2. Okay? Now, if we were going to do this by hand, I would suggest rewriting this as 2 radical x dx for this integral. And then I would suggest multiplying that subtraction through the x minus 2. Okay? But I'm going to go ahead and let you use your calculator to find this area since it's 2 integrals. And it's a Wednesday.
It's also game day.
It is game day. Have a better team's arena.
Yeah. 1-0 this season against him. I don't think DJ Johnson's playing either. He's hurt.
You have it?
Well, no, I have a
Oh,
question.
okay.
Can you, like, for the integral, can you use different numbers or different, like, functions? Like, could you use x minus 2 and negative radical x to find it? Oh, wait, never mind. You have to be above function.
Yeah, it has to be top minus bottom.
Oh,
so
right,
like,
then that would be 3 functions.
yeah, yeah.
That would be
If your top and bottom function change at all, you're going to have to split it into 2 different or more integrals. Okay? Does anyone have this area? What do you got? 9 halves. Yes.
How come in the first one we're doing it from 0 to 1, the one that's from 0 to 1?
Uh-huh.
Where do we get that b value from?
Because, okay, so we start at 0, right?
Mm-hmm.
And then here at x equals 1, that's where our bottom functions switch. So until 1, the green function's on the bottom, but then after 1, the blue function's on the bottom. Does that make sense, or do we need to talk about it again?
Well, I thought after 1, the blue was on the top.
No, the blue one's still on the bottom, because we're finding this yellow region, right? So the red function is always on the top. See, look at the rectangles, and this is why we draw the rectangles. Because our rectangle's top is on the red function all the time. But this one, the bottom of it is on the green, and this rectangle, the bottom of it's on the blue.
Oh, okay.
Okay? So we look at where those 2 intersect to know where they change. Okay? Now, something like, see if I can draw it. What did I just draw? I drew a sign. And that's a cosine, right? So if I wanted, like, the area from 0 to 3 pi over 2, notice how the top function changes, the top and bottom function change how many times? 3. We would have to find 3 different integrals to represent this area. Because here, let me highlight, cosine's in green, okay? Here the cosine is our top function. But between here, cosine is our bottom function. And then here, cosine's our top function. So you see how they switch? So we'd have to have 1, 2, 3 different integrals to represent that area. Okay. All right, I'm going to hand you your gold sheet, and then you're going to mark which ones I want you to do with and which ones I want you to do without